So today we're going to get into more discussion of collisions and momentum. We're going to talk about a couple different types of collisions. So while you're working through this video, you should have your notebook handy. And when I give you a concept check question, you should pause the video, think about it, select the right answer, and then check to see if you're right. If it's a numerical problem, you should try to work it out the best you can on your own, and then listen to my explanation to see if you're on the right track. That's a really good practice. So have your notebook handy, pause this video if you need to go get it. Okay, so here we go, collisions and momentum. First kind of collision we're talking about, it's not really a collision, it's more of an explosion. And we actually talked about this yesterday with the person on the cart and the medicine ball, or a cannon. The idea is you have something that's initially at rest. So the total momentum of the system at the beginning is 0. And then after you fire something, the total momentum of the system is still going to be 0. So the idea is you take your ball and you shoot it, it's going to have momentum mv, and then the cannon is going to have the exact same momentum going the opposite direction. Obviously it has more mass, so it's going to be moving less fast, the cannon itself, where the cannonball is going to be moving really fast. So if you add these two momenta together, they should add up to give you 0. So that kind of a collision is called an explosion. Okay, types of collisions. You have inelastic collisions and you have elastic collisions. So inelastic, think sad bounce. Another example is a golf ball that's dropped that does not return to its original height. There is some energy lost when that ball hits the floor. There's sound energy, there's heat energy, a little bit of heat loss, so it doesn't rebound to its original height. When you have inelastic collisions of carts or cars or things crashing into each other, there might be some element of sticking together, like they stick together before they come apart. So that is called an inelastic collision. And an elastic collision, think really the happy bounce ball, okay? In this case, mechanical energy, especially kinetic energy, that's the one we talk about in collisions, is conserved. So whatever energy you had before the collision, you're going to have the same amount of energy after. So we talk about a perfect bounce. So an example you see in our lab is when you have the two carts that have magnets, and so they get close to each other and they push each other apart. Those are elastic collisions, or we call them perfectly elastic. Okay, demos, obviously not going to get that in this video. We'll save those for when we get together in class. So a perfectly inelastic collision is a special kind of inelastic collision. This is a kind of collision where two things come together and they stick and they move off together. So what we have here is two carts, and you have this one moving this way and this one is not moving at all. They come together, they link up, and then they travel together. That is called a perfectly inelastic collision. It's where the two things are stuck together at the end. Now the math works out pretty nicely when you're doing a perfectly inelastic, because you just say, well, whatever the first momentum is plus the second momentum, in this case the second momentum was 0, right? You take those two and add them together, and then the two masses are going to be traveling together at the same velocity. So there isn't like a v1 prime and a v2 prime, there's just a v prime, because they're both moving together. So those are pretty straightforward to solve. So if you have a 4 meters per second, let's say that these are the same mass. If you have a 4 meters per second and a 0, then together they're going to go off at 2 meters per second. Again, this is assuming that both those trains have the same amount of mass. Okay. So perfectly inelastic collisions are where two items stick together. Think Velcro. Car crashes are when two cars might meld together and then travel together. In this case, what happens to the energy is dissipated as heat, as sound, mostly heat, but the energy is lost to the atmosphere. It's not saved. What happens to momentum? In every collision we talk about, momentum is conserved. Okay, momentum is conserved. Momentum is always conserved. As long as you have a case where there's no external forces, two things crash into each other, momentum is conserved. Now we say this is an extreme case because this is a case where the two things stick together. We'll talk about the other types of cases as well. So, solving problems in a perfectly inelastic, again, the initial momentum of the system is going to equal the final momentum of the system. And you just got to sum them up and solve for what you don't know. So you take the m1v1, m2v2, and know that both are going to travel off together at the same final speed. So here's an example problem. So again, get your notebook, try to write this down, and try to work it out ahead of me. Now, start with me though. The first thing you want to do is make it a little diagram. Get a sketch. It'll help you keep track of what's happening. So I have my 2 kilogram, and it's going to the right at 4 meters per second, and then I have my 6 kilogram, and it's going to the left at 1 meters per second. and then they're going to stick together because this is a perfectly inelastic. So the question is, how fast are they going to be going? So we're going to use our conservation momentum, and we're going to solve the problem. So go ahead and try to set it up and solve it on your own, and then come back to the video and watch how I solve it. Okay, if you're back, that means you tried to solve it. Once again, the two things are going to stick together and move at some final velocity. I don't know what that is, so let's work it out. I start by setting up, I have my first momentum over here, 2 kilograms times 4 meters per second, and the initial for the other one is 6 kilograms times -1 meters per second. That is the sum total of the momentum, and that's got to equal the two masses together going off at some new velocity. So let's figure out what that velocity is. Now we're just going to do the math, and we get 8 kilograms minus 6 is going to equal 8 kilograms times v prime, so 8 minus 6 is 2. And so we're going to get 2 kilometers per second divided by 8 kilograms, which is going to give us our final v prime of 1/4 meter per second. Okay, and that should make sense, right? Because the 6 kilogram has 6, this has 8. When they stick together, they're going to be a lot more massive. They're not going to move very fast, so they're going to go to 1/4 meter per second. And that's positive, by the way. So that means the total final velocity is going to be to the right. And that should make sense because you can see initially the one this guy over here has more momentum. It's got 8, and this one's only got 6. So the 8 is going to win, and it's going to end up momentum in the system is going to go to the right. Okay, moving on. All right, a skater moves horizontally with no friction at an initial speed v. Okay, a package is dropped vertically into her arms. Her speed after catching the package is what? A, v, b, more than v, c, less than v. Okay, pause the video and try to figure out what you think it is. Okay, here's the governing equation. The initial momentum of the system has to equal the final momentum. Now, initially a skater was moving at some speed, m1, v1, but then we just drop into her arms a mass that doesn't have any velocity associated with it, so it doesn't have any momentum. So basically the skater is now carrying more mass, but the total momentum, her total momentum has to be the same as it was before. So this momentum has to be the same as this momentum. So given the fact that she's now got more mass, it makes sense that she would slow down. So her speed after catching the package is less than v. Okay, next question, different question. A skater moves horizontally with no friction at initial speed v while holding a package. If he then drops the package, his speed after the drop will be what? Okay, stop the video, think about it. Okay, now you might get confused in this one because you think it's the opposite of the one from before, but it isn't. In this case, he starts with a momentum, he has extra mass, right? And then he drops the mass. But remember, it's a frictionless surface. So basically what's going to happen is the mass, the little mass you do, maybe the little package, M2, it has some speed associated with it. And so when you drop it, it's going to keep that speed. Like a body in motion remains in motion unless asked upon by an outside force. So if he just drops it, it's going to keep skidding along just like it was before. And so what's going to happen to you, or the skater who drops it? Absolutely nothing. He's going to be keeping going at the same speed he started at. So in this case, after he drops it, his speed will be v. Now, could you figure out something to do with the package to make yourself speed up? Yeah. If you were holding a package and while you skated, you threw the package behind you, that would propel you forward, kind of like the balloons in the rocket with the air, right? Or if you were skating along and you threw the package in front of you, that would cause you to slow down. But if you just drop it, you're going to both keep moving together at the same velocity. Okay. A block of mass m moves initially at speed v across a horizontal surface. It then collides and sticks to a block of mass 2m that was originally at rest. After the collision, they will move together at what speed? Okay, pause the video, try to figure it out. Okay, so again, I'm going to make a little sketch. I've got a mass moving at a speed v, and I have another mass that's 2m and doesn't have any speed at all. So the total momentum of the system beforehand is going to be 3m, was going to be mv, right? So let's just work this out. So the total mass is going to get mv is the momentum of the red box and 0 of the purple, and that's got to equal 3 times m, times the final velocity. So, given the fact that you started with this much momentum, and you have 3 times the mass together, and it's moving at some new speed, you could then solve for that new speed, and it turns out is 1/3. So v over 3. So the answer is 1/3. Okay. Using conservation momentum to determine speeds before or after a collision. All right, so we're going to use momentum and energy. Kinetic energy we can also use to calculate any changes in energy, and that's going to reveal some information if we lose energy or if we don't lose energy. So, first of all, momentum. Here's your momentum equation. Momentum is always conserved. Okay, momentum is always conserved. So, determine speeds before and after collision. You use m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. You're given some masses and some speeds. You can find the missing ones. You can also find the change in kinetic energy. Remember that kinetic energy is kinetic energy final minus kinetic energy initial. So, final energy is going to be 1/2 m1v1 prime, or final, squared, plus 1/2 m2v2 final squared. So the final energy, that's the final energy right here, minus the initial energy. So we're going to ask you to calculate both what are the speeds that are missing and then what is the change in energy. So here's an example. We're going to work it out in detail. Please try to do this in your notebook. Try to stay a little bit ahead of me. Okay, 3 kilogram cart moving to the right at 4 meters per second makes a collision with a 6 kilogram cart moving to the left. After the collision, the 6 kilogram cart moves to the right at 1 meter per second. A, find the final velocity of the 3 kilogram cart. Okay, we're going to use momentum to do that. Then B, find the change in kinetic energy. So, pause the video, make a sketch, keep track of everything that's going on, and try to solve the momentum problem. Okay, just the momentum problem. So make a little diagram of things moving left and right. They collide. They're not going to stick together. The 6 kilograms is going to go to the right, and you don't know what's going to happen to the other one. All right, so solve for the other one. All right, here we go. I'm going to solve it now. Here's my diagram. I got 3 kilograms and 4 meters per second going to the right. I have 4 meters per second and 6 kilograms going to the left. And then I know after the fact that 6 kilograms is going to be going at 1 meter per second to the right. So there's my diagram. Okay, so here is my equation. I have 3 kilograms times 4 meters per second. That's positive because I'm defining to the right as positive. Plus 6 kilograms times negative 4. Okay, so this is the original momentum of the system. Okay, initial. Notice I have a negative 4 because that one is moving to the left. And that's going to equal 3 kilograms times v1 prime. I'm trying to solve for v1 prime. Plus 6 kilograms times positive, it is positive because it's moving to the right, times positive 1.0 meters per second. Okay, so now I got my numbers. I'm just going to solve for v1 prime. So algebra, 12 minus 24 minus 6. I get negative 18 kilogram meters per second. I know I'm going fast, but hopefully you already solved this. Divided by 3 kilograms to solve for v1 prime, and you get v1 prime is negative 6 kilograms meters per second. Okay, v1 prime. So the final speed of that little, the purple one is going to be negative 6. So it's going to bounce backwards and go faster. Okay, now I'm going to summarize everything that we found on this first page. So I've got my mass, my velocity before, and my velocity after the collision. So the 3 kilogram mass starts off at 4 and ends up at negative 6. The 6 kilogram mass starts off at negative 4 and it ends up at 1. Okay, now I'm going to grab all that information because now we're going to solve part B. Find the change in the total kinetic energy. And this is just tedious, but it's not hard. You just have to be really careful with your accounting. So here we go. So this is part B. I want to find the change in kinetic energy, which remember is kinetic energy final minus kinetic energy initial. So 1/2 mv1 prime squared plus 1/2 mv2 prime squared, because that's the final kinetic energy, minus 1/2 mv1 squared plus 1/2 mv2 squared. Okay, so this represents the initial kinetic energy. I'm sorry, the final kinetic energy, and this represents the initial. And now we're just going to plug in our values that we have. So let's remember what they are. And so we've got from the other side. So we're going to get delta KE. Change in kinetic energy is just going to be 1/2 times that 3 kilogram times negative 6 meters per second squared. Okay, I'm going to pause the video right now. Okay, I got you started. I got you the first value. Okay, 3 kilogram is the final speed, which is -6. I'm squaring it, plus 1/2, and you're going to be, now you're going to have the 6 kilogram times its speed. So I want you to go ahead and finish this, right? Set up the total change in kinetic energy and try to really carefully work it out. Be very careful with your signs and come up with an answer for the change in kinetic energy. And once you get it, then come back to the video and see the final result. Okay, I got you started. Find the change in kinetic energy. Okay. All right, so you're back. Here it is, all of the math in all its glory. Remember, energy is in joules. So when you evaluate 1/2 times 3 times 6 squared, so that's 36 divided by 2 times 3, I get 54 joules plus 3 joules. Again, this represents the final kinetic energy. This represents the initial. Notice it had more energy to start than it had to finish. What does that mean? Well, let's finish the problem. And we get a total of -15 joules. So that means the change in kinetic energy was a -15 joules. That means in the collision we lost energy. Okay? It was not zero change. It was a loss of energy. And that's because in the collision there was heat or sound losses. There was energy lost in the process. So this would be called an inelastic collision. Now, I would not say it's perfectly inelastic because we know that the things did not end up at the same speed together. But because energy was lost, we say it's an inelastic collision. Okay, moving on. A small car makes a head-on, perfectly inelastic collision with a large truck. Which vehicle has the larger change in momentum? Okay, a couple ways to think about this. Here's the first way. First of all, if you think about a car and a truck crashing into each other, there is going to be extreme forces. But the forces that each are going to feel are going to be equal and opposite because of Newton's third law. And the delta T is going to be the same as well. So the F delta T, the force on the car over the period of time, is going to be exactly equal and opposite to the F delta T on the truck. And so if the car and the truck have the same impulse, then that means they must have the same change in momentum, because F delta P is going to give you a delta P. So from that reasoning, you could argue that the change in momentum of the truck is going to be equal and opposite to the change in momentum of the car, which seems strange because like truck seems like it has more mass, but no, it's going to have the same change momentum as the car. Now, I'm going to brute force it for you now and work it out mathematically, okay? It is a perfectly inelastic collision, so I can write the equation to look like this. I have the mass of the car times the velocity of the car plus the mass of the truck times the velocity of the truck equals the mass of the car plus the truck times v prime. Now, if I keep through, this is like a little proof for you, right? If I multiply it out, so that we get vc times v prime and mt. Now I'm going to get the masses of the cars together and the masses of the trucks together, so I'm going to rearrange. And remember that the change in momentum of the truck is just the final velocity of the truck times its mass minus the initial velocity of the truck times its mass. So keep going here. I rearrange and I get the trucks on the left side and the cars on the right side, and lo and behold, what do I find? But that represents the change in momentum of the car, and on the purple is a negative change in momentum of the truck, so they are equal and opposite. So two different ways of thinking about what's going on, right? So small car makes a head-on collision, and they're both going to have the same change in momentum. Okay, now let's talk specifically about elastic collisions, also known as perfectly elastic collisions. In a perfectly elastic collision, we say that the total kinetic energy is conserved. That's what's really cool about them. So the kinetic energy initial is equal to the kinetic energy final. So we have two equations we can deal with. We have the momentum equation, because momentum is always conserved in every collision, whether it's inelastic, elastic, or perfectly elastic. But in this case, now we have another equation. 1/2 m1v1 squared plus 1/2 mv2 squared is equal to 1/2 m1v1 prime squared plus 1/2 m2v2 prime squared. And that sets up some interesting situations, especially if you're talking about things that have equal mass. Now, I put a little spectrum up here at the top corner, right? So up here, you have basically the extremes. You have a perfectly inelastic collision is when they stick together. And then on the other extreme is a perfectly elastic collision, which is where they perfectly bounce and don't lose any kinetic energy. And then inelastic collisions are everything in between. So that's what's going on there. Okay, so cool special cases. If it turns out that your masses are identical, like you have billiard balls that are crashing into each other, if you have a situation like down here where you have one ball that's moving and one ball that's stationary, if it comes in and it crashes and it doesn't lose any energy and you have a conservation momentum, that what happens is after the collision, that first ball comes to a dead stop and the second one takes off with the same velocity of the first one. Now this is a one-dimensional problem. What we have here is two different sets of equations. So you find that v1, the initial velocity, is equal to v1 prime plus v2, and v1 squared is equal to v1 prime squared plus v2 squared. That leads to something interesting in 2 dimensions here, and I'll talk about in just a second. Now we'll do some demonstrations when you get back to class of different balls crashing into each other, and we'll see how this works. But here's the kind of the theory behind it anyway. All right. Demos. Here's the ones we're going to look at tomorrow in class. Concept question. A golf ball is shot horizontally at a bowling ball, which is initially at rest. The golf ball rebounds with close to its initial speed after making an elastic collision, and friction can be neglected. After the collision, which ball has a greater magnitude of momentum? Okay, magnitude of momentum. Which one? The ball, golf ball, or the bowling ball? So stop and think about it for a second, and then come back, and let's think through it together. Okay, here's the original scenario. You have a golf ball coming in. It has a speed, mv. You have a bowling ball, which is way more massive than the golf ball, and it is just hanging out. It's not moving. So you might say it has no momentum to start. And then you have the golf ball bounces, and it comes back at essentially the same speed, right? And so the original momentum of the bowling ball was 0, but now the bowling ball is going to have some momentum. The question is, how much momentum will it have? And how will its momentum compare to the momentum of the golf ball? Okay, so let's work it out. If we talk about the momentum of the system before, then we have mv, that's the golf ball, plus 0, that's the bowling ball, equals minus mv, because now the golf ball is moving the other direction, plus, well, we don't know what the mass is, but we're just going to call it the momentum of the bowling ball prime, in other words, after the collision. Okay, so then we're going to solve for that momentum of the bowling ball. What is it? Well, if we do the math, we're going to get it's 2mv, because you have the mv over here plus or minus a negative mv. When you move that over, so you're going to end up at 2mv. So what is the magnitude of the two different momenta? This one has a momentum of mv. This one has a momentum of 2mv. So which one has a greater magnitude of momentum? It's the bowling ball. Kind of unexpected. Okay, so this is kind of cool. Two-dimensional collisions. Now, we're not going to have to do any of these mathematically. They're just fun and interesting. If you have two cars coming together at a right angle, they're going to hit and they're going to stick together. So if you just add the vectors of momentum, so you take, here's a momentum vector of one, and here's a momentum vector of the other. If you add them together, you're going to get the momentum vector of the system. So the momentum of the system before the collision is going to equal the momentum of the system after, which is why when they come together and stick, they're going to go off at an angle like that. It's kind of cool. Okay, another little artifact, if you have two masses and they're the same quantity mass, so m1 is equal to m2, if the masses are the same, and you have a ball that comes in and it strikes a ball kind of on the side of the ball instead of dead on, so it's a two-dimensional type of a hit, like think pool, right? You take a ball and you hit another ball, but you hit it off to the side. It causes one ball to ricochet off this way, and then the ball that you hit bounces off that way, right? So here's a really cool thing about that. Because momentum is conserved, right? So v1, the vector, the v1 is going to be equal to v1 prime plus v2 prime. You add those two vectors. v1 prime is going to equal the sum of the two, right? So here's v1 prime, and here's v2 prime, and that's going to equal v1, right? Those two are going to add up to v1, but because v1 squared equals v1 prime squared plus v2 prime squared, then we know that this has to be a right angle. I'm going to get rid of that because it's kind of hard to see. Let's keep going. So because you get this v1 squared equals v1 prime squared plus v2 squared, then you know that the outgoing vectors, this vector and this vector, are going to be at a right angle to each other. And so that's really useful when you're playing pool, right? So if you aim, then you know that whichever way your ball goes, your cue ball is going to go off at a 90-degree angle. So you can plan ahead when you're shooting your cue ball. Another special case of elastic collisions, if you have the same mass of carts. But if you have two different velocities, let's say this one's going really fast and this one's going kind of slow, okay? And they're coming towards each other. What'll happen is when they collide, they will exchange their speeds. So this one came in fast, now this one's going to go off fast and this one's going to go off slow. It's pretty slick. So the carts will actually switch velocity. Again, that's a special case when you have elastic collisions. And we'll demonstrate this in class. Okay. That kind of concludes our lecture. We will work problems together in class and show you a bunch of demos and be ready to go. Thanks for listening.